So thank you so much, Carl. Thanks for making it work to join us remotely. And I think what we'll try to do for questions is if you have questions, maybe you'll just come up so that the OWL microphone hears you well. And microphone, speaker. I think we're good. Okay, Carl, thank you.
Awesome, thank you. Hopefully everyone can hear me okay.
Yeah, the sound is great.
Okay, cool. Yeah, I appreciate everyone being here. And thank you to the organizers for inviting me. Sorry I couldn't be there in person. I'd love to join you all in person in the future, but thanks again for pivoting to this remote fashion last minute. So today I want to talk a bit about, and I was told 30 minutes for a talk and 30 minutes for questions, so I'm going to keep it around 30 minutes. So we can have some discussion at the end. But today I want to talk a bit about the work that I've been doing, which I've sort of been coining in sort of proposals and different types of things as the next generation simulations of the remarkable deaths of massive stars. And so I'm going to try to highlight some of the ways that we're looking at these different things and how they connect to different areas of astronomy. And so I want to start off by talking about an overview, so presenting what I'll be presenting. So I'll start off by talking about core collapse in general, so bring us all to the same page about some of the ideas that I think about when I think about core collapse supernovae. I'll talk about current core collapse models, some of the state-of-the-art methods that folks take, some of the approaches that are used within these different realms. And I'll also present some problems, some of the things that keep me with some sense of job security and some possible solutions that folks have proposed in our subfield and different things that people are pursuing to address these issues. One of the things that I'll talk about in particular is a lot of the work that I've been doing looking at three-dimensional core collapse supernova progenitors. And so looking at the stars that will eventually produce the stellar explosion, what those stars look like deep within that stellar interior near collapse. That's going to lead me into talking about a landscape of 3D progenitors that I've explored. It's going to lead to me talking about rotation. There's always those two things, rotation and magnetism, that people talk about. We started to look at rotation. I'll highlight some of the results that we've gotten from those models. And one of the last things I'll talk about, I'll touch on briefly, are the implications for multi-messenger signals from core collapse supernovae that leverage multidimensional, in many cases three-dimensional progenitors, and how that varies from sort of the standard paradigm of using strictly symmetric initial models or some other hybrid form. So starting off talking about core collapse supernovae, so that is the death of a massive star. It is one path a massive star can take. And so it can produce some sort of stellar transient. We have core collapse supernovae. These other type of transients that I list here that all have different various features. One of the great things about these is that they leave behind compact objects. So they have, there are times when they can produce neutron stars, stellar mass black holes, all of which sort of set up the next generation of yet another stellar transient. Say, for example, in the case where you have two neutron stars that eventually merge, or other such scenarios. And so they're very important in understanding, what are the properties of these stellar explosions and how can we determine what type of compact object it will leave behind, and we fold that back into our other models of compact object formation. They're also very important for galactic chemical evolution. So we think about stellar nucleosynthesis as well as feedback. They play a very important role in both of these different processes. So understanding how these work within this context is also very important. And lastly, multi-messenger astronomy. So they produce signals across different types and many different types of ways. Some of the ways that I think about them are gravitational wave signals, neutrinos, of course, electromagnetic waves. And so there are a lot of ways that the death of a massive star will play a role into various different subfields of astronomy, which really motivate a deep understanding of how they work. And so generally speaking, we expect about 3 per century for a Milky Way type galaxy. And one of the characteristics of these is that they generate a ton of neutrinos, right? So that's really great about them. And they also have kinetic energies on the order of about 10 to the 51 ergs, 1 beta, and they're produced by stars about 8 times more massive than our sun. And so these are sort of the regime of stars that we expect to end their life as core clouds.
can do is I can help moderate just in case. But if you have questions also, it might help if you either come up or depending on what you can hear, Carl.
Sounds good.
So go ahead, I'll go ahead.
Hi, Carl. That was a nice talk. This is Kareem. I was just wondering about when you set up these flash models based on a MESA model. I guess you have to map 1D to 3D somehow, which has it seems like there's more than one unique way to do that. So can you talk a little about how you do that, and do you seed any inhomogeneities, or where do they come from?
Yeah, thanks. That's a great question. So in terms of the progenitor models, what we do is we'll take a MESA model, and there's a method that folks use. I think it's a Myers-Singolic paper from mapping to a code like Flash, where you take something from like a Lagrangian framework, you map that into 1D. So essentially what we do is we enforce hydrostatic equilibrium when we map it onto the domain. We initialize all of the variables as being, they're spherically symmetric initially. So that's sort of our starting point on the new domain. And then from that, at first we didn't add any sort of perturbations to our simulations of perturbations or anything like that. We kind of just let the Cartesianness of the grid sort of initialize convection. But something that'll do is that'll give you a very sharp peak at L equals 4 along the grid axis. And so we realize that's not a good idea. And so what we do now is we use those spherical harmonics to initialize the velocity field for a given shape that we expect to see within these shell regions. So we sort of ping the model, if you will, the velocity field, and then allow it, the convection, to tend towards its natural state after that. So that's how we do that now, to avoid it tending towards the Cartesianness in scenarios where there is weak convection.
Yeah, can we follow up on that? I was curious, okay, so for example, does the minimum order that you put power in matter? Like if you put power down to L of 8 versus L of 4 versus L of 2 or 1, do you get different sort of global morphologies in those structures?
Yeah, no, that's a great question. So we noticed that a little bit with the, let's see, I'm not used to using PowerPoint, so I have to do the sort of manual going back. So that's a bit what we noticed here. So between these two, the difference was I think we used like L of 7 in the top panel and L of 11, so smaller scale initial velocity field perturbations. And we did actually observe a slight difference here. In the top panel with the larger scale, we showed more material being mixed down. And so we are arguing that, because this is a detail I feel like that a lot of people that do these simulations maybe don't pay much attention to, and we're arguing here that it can make a difference in the mass entrainment of these different properties. So it's something that at least should be taken into account when initializing these models and then making estimates about what the convective properties are. And so, yeah, it does make a difference. It's a small difference, but it's one that maybe is big enough for things like galactic chemical evolution.
Well, what about even lower orders? So my understanding is, say, from the 1D, like our convective Mach number, your L equals 1 power, if there is any, isn't really something you would know ahead of time. But if there is a dipole moment in that convective field, even if it's a smaller than, say, one of these other powers, doesn't that give you the sort of morphology like you were seeing in that intermediate 20 solar mass model, where you get sort of these oscillations between inflow and outflow? Maybe you can talk a little bit about that.
Yeah, no, that's a great question. So, so what we've done in the past is we've avoided using very large scale modes to our spherical harmonic degree to initialize these, because we basically, we base these initial perturbations on a couple of things. We base them off of, for one, we normalize the scaling factor that we use to be a fraction of what the convective velocity is at the model at the time it was mapped in. So we choose it to be about 5% of that. So these are like 5 to 10% level perturbations on what should already be an existing velocity, speed, or field, according to MESA, that is. So they're pretty weak in terms of the initialization. And we also want to initialize them to what we expect the bulk of the energy to be in a lot of these different places. And so we start with something that's sort of in the middle of these kinetic energy spectra that the folks are seeing in these different shells. But I do agree that if you start off with something that's you dump all that energy into the sort of larger scales, it's probably going to stay that way from the beginning. So that's one of the things that we're seeing. So, and you know, we also noted too that in some of these simulations, you know, the shell width matters, and so for the silicon shell convection, we're seeing a much different spectra. Because it's just much more narrower, and so you can't grow to these large scales like you can in the oxygen shell region. I think that's why it's so important to survey some of these different shell widths, because I honestly feel like once you lock in what that width of that shell is, there will be some, you know, deterministic sort of larger scale that you can.
Yeah, so maybe the larger scale mode depends on, you know, how many can stack around the. That's one.
Right, exactly. So, yeah, so we do that analysis in the paper. I forget the name of the equation, but we were able to make some estimate for that. But yeah, so it does. Those shell widths are super important.
Amazing. I think maybe Avi had a question.
Can you hear me?
Yes.
Yeah.
Okay. Very nice talk. Can you elaborate on the significance of one of the uncertainties, which is neutrino mixing, because that could potentially play a role. Some people examined it, and what do you think, you know, how important that could be?
Yeah, that's a great question. I think that I think there's a lot of work to be done in terms of flavor oscillations, in terms of the neutrino transport, and I think a lot of people are pushing on that. I think it's really hard to do, and I think that I'm glad that a lot of other folks are working on it. But I think right now, in terms of where folks are placing their emphasis, I think people are trying to move beyond a moment-based approach to neutrino transport, and so truncating these, you know, these truncated attempts at solving the complete Boltzmann equation for neutrino transport. And I think that's where people are really pushing on it the most, is trying to get a piece of the neutrino transport that's being approximated now in higher fidelity. And I think that's what people have been placing higher on the list. But I do think that there are other corrections due to things like flavor oscillations and so on that are also equally as important, but I think are just very hard right now with the current way that things are in terms of the transport. So I think it's also up there with those uncertainties, but it's one that I think is making less progress at this time.
Thank you.
Thank you.
Other questions? Yeah.
Are you able to predict from these simulations whether you'll get a neutron star or a black hole at the end? And if so, how do those predictions compare to what people measure just from like the compactness of the MESA model?
What was the last part of the question? I'm sorry, I heard most of the.
Yeah, so like how does the, if you are able to predict the sort of compactness of the collapsed thing, how does that compare to like the compactness parameter from the 1D models, like in an.
I see. The compactness parameter, yeah. So that is something we looked at in one of the, I think in each of the papers, we've looked at the difference in the compactness parameter. It's not much. It is slightly different, but it's not much. The thing is, once you kind of have like sort of the fixed because my understanding of the Packness parameter, it's sort of just as I think I've heard Frank Timmy's referred to it as a measure of the depth of the gravitational potential or something
Right.
along those lines. You don't change that much with these simulations. You're mainly changing sort of the composition of these different shells as things are mixing up and becoming turbulent. But in terms of the density sort of profile, it's pretty fixed. What we're finding to be potentially more of a change, as opposed to the compactness, which I thought I initially thought would be more significant, is that the angular momentum transport, the redistribution of angular momentum in models that are rotating. And so that's where we started to lead into, okay, well, compactness is pretty set based off of what we're seeing right here on the scale that we're doing these simulations. But that angular momentum can really get mixed up on a time scale that is pretty short. And so what does that say? Potentially, like you said, about what objects are formed, because if you have a ton of material interior and you have something that's very close to that mass transition, then you could potentially create something in 3D that you can't based off of 1D estimates. So that's sort of where I'm seeing it. So I'm talking with folks that are interested in angular momentum and how that looks near collapse. It's not something I've quite worked on post-explosion, I guess, in terms of some of these models, but it's something that our models have implications for. We're really interested in starting to look at.
Thanks.
Okay. Josh?
Thank you.
Can you use what you were just mentioning about angular momentum transport to make predictions for, if it is a black hole, what the spin would be?
Could you hear that, Carl?
I heard most of it. If I could
Yes.
make a prediction for the spin of the black hole,
Yeah.
That's right.
I think that's something folks want to do. I think it really does depend on the angular momentum profile near. So I mean, there's the profile at collapse, and then there's what that profile will look like, or that distribution will look like post-explosion. I think that those are two different pieces right now. That's really hard. But I think, given two simulations of all those things, I do think that one could make that estimate. I think that's something that's very doable. I know a lot of people use different semi-analytical approaches and sort of approximate equations, scaled relations, and so on. So I think if we had just new numbers to plug into those things, we could maybe provide new estimates in that way. But I kind of want to move beyond that and sort of do something that's a little more detailed, self-consistently from these simulations. I think that's what we're really excited to try and do, connecting these pieces of pre-collapse, explosion, and post-explosion. Which is why we're really excited about Phoebus, because it runs on GPUs and is very fast, and so we're excited about this new code.
That's wonderful.
Morgan,
Yes.
one more question. Do you have anything to say about the kick that, for pulsars can be measured and how that relates to the initial conditions?
Yeah, that's a great question. Not yet, but that is definitely something we want to do. What are the implications for a model from exploding from a 3D initial condition, following that out long term? What does that proto-neutron star kick look like? And does that have a different orientation, magnitude, velocity, all these different things based off of the 1D spherically symmetric model? That's not something we've looked at yet. Folks have done it for I think a particular model. I think Bernard's group made an estimate for I think in 2021. But I think that there's still a lot there left to do, as there being some implications for what these 3D progenitor models do for the kick. So I do think that that's a key piece that we want to try and take out when we run these next generation 3D explosion models. So.
Amazing.
Thank
Carl,
you.
I thought maybe as we close, you could give us just a few thoughts on, I think for a long time the sort of thought, at least, was that a 3D model is harder to explode than a 1D model because you have more degrees of freedom, kind of thing. Like the explosion can wiggle around rather than necessarily going out. Why is it that now when we add this extra dimensionality in the pre-explosion conditions, we're kind of going in the opposite direction. Like, why should we change, like, how is it that we need to think about that differently? What's wrong with that original thought?
Yeah, I think that I think it's the case that 2D models have always been easy to explode for the same reason, just the less degrees of freedom, the inversion of the turbulent cascade. You just have things that naturally tend towards that just make it easier to explode.
Right.
I think it's the case that in 3D there are much more subtleties that there are many more subtleties that have an impact where now you have to, because you're not artificially sort of enhancing the turbulence, you have to make sure that neutrino transport is proper. You have to make sure gravity is treated correctly. You have to make sure that you have a idea of what the star looked like in your collapse, because that material, what that material looks like as that shock traverses through it is going to alter the convection that's behind the shock. And so I think now, because we're able to do 3D explosion models, it is no longer appropriate to rest on the approximations that were sufficient for 2D, because 2D kind of, you know, would just sort of explode in many cases for many approximations. So I think that's one of my main takeaways, is that now we have to do the hard work. Now that we've gotten to the point of being able to do 3D explosions, 3D hydrodynamics, because of the new technology and the new methodologies. And I think now we're going to have to go back into the drawing board, and so, you know, get a better treatment for GR, get a better treatment for neutrino transport. And that's what a lot of folks are really pushing on, and taking advantage of GPUs, because people don't want to give up their CPU codes.
Totally. Well, thank you. Maybe everyone, we can thank Carl one last time.
Thank you. Yeah, I appreciate it. Thanks again to the organizers. Sorry I couldn't be there in person, but I guess y'all will see me again. Some of y'all will see me again when I chat about this web soon. So.
Amazing.
Carl, we're going to try to use the same link, so we'll see you at about 25 after.
Okay, 25 after you said?
Yes.
So 30 minutes? Okay.
Yeah.
Okay, sounds good. Thank you.
Thank you. This is really wonderful. We're muted. And thanks for letting us use your computer.
So much better than Lisa's.
That was successful. Yeah, more successful. Yeah.
Did you see Lisa's talk?
No.
You put a TV slide.
Oh no. That's hi, Josh.
Really pretty bad.
So what's the schedule?